Right. So both my talks are just going to center around a single question. So it was a conjecture which was answered a couple of years ago. So let me write that as a reference. I'll spend quite a bit of time, of course, first of all, explaining what these terms mean, mainly what Teichmuller space is, and then why would one even make this conjecture? So what was the context of this conjecture? That's something I'll try to explain. And yeah, right. In fact, there is a... So this was a long-standing conjecture, maybe at least for some 20 years, made by Siu, but various others as well. It was a kind of folklore conjecture. Around the same time that my colleague Shubhajay Gupta and I started looking at it, it turned out that Markovich also had been looking at it for much longer times, and he arrived at the solution. In fact, I didn't know that he had, since he didn't post on the archive, later on when I went to Japan, I found out that he had put the solution on his homepage some 3 or 4 months before ours. Well, anyways, that's not so important. But the point is, it's interesting that around the same time, the other mathematician Gardiner, who's a well-known guy in Riemann surface theory, had his own proof of the same result, which was even later than ours, as it turned out. So it's interesting that something which was dormant for almost 20 years, within a space of a year, 3 different proofs addressed this, proved this. But that happens quite a bit. So let me so in this talk, basically, I would like to focus on Teichmuller space as a complex manifold. And that's one aspect of my talk. And the other one is, of course, this is already a domain in Cn, but the key point here is the convexity. So what does this entail about the complex geometry of the domain? So I'll start with the easier part. This is the complex geometry of convex domains. So let's quickly recall the standard intrinsic metrics. The Kobayashi and Karthaderi metrics on these domains. So on any bounded domain, we have the infinitesimal Kobayashi metric, which is actually a Finsler metric defined by in the usual way. Look at all holomorphic maps into the domain and so on. Then the distance function associated to this Finsler metric is what is usually called the Kobayashi metric. So the moment you have a Finsler norm, you can talk about length of curves. And then, yes, just like in Riemannian geometry, you would just take 2 points, look at all piecewise smooth paths connecting those two and take infimum of all lengths. Standard procedure. Though I must say that when Kobayashi originally defined this, it's interesting that this thing here was not yet there, I believe. Kobayashi directly defined this without going via without having the infinitesimal form. This is, I mean, it's somewhat more cumbersome thing, slightly more cumbersome thing. One has to look at chains and so on, chains of open sets connecting 2 points. It was Royden who subsequently came up with the Pfinsler metric corresponding to this. This, on the other hand, is easier to define. I have not written the Pfinsler form here, but even that's rather simple. The Cartesian metric as a distance function is just defined by look at all holomorphic maps from the domain or complex manifold to the disk, and then just look at where 2 given points go and measure the Poincare distance and take the sup. The only catch is that while this, the previous one, whatever complex manifold you start with, you can always find non-trivial holomorphic maps of the disk into the manifold satisfying these conditions. But here, the existence of such a map already entails something about the domain. I mean, for example, so in particular, you would have a bounded holomorphic function on the domain. For this to even make sense, you would need to have a non-constant, that is, non-constant bounded holomorphic function. So, for this to be even a well-defined distance itself, it's when you're especially dealing with in the manifold context, in the domain, even unbounded domains, for this to be a metric itself is not so clear. Yes, it's not. But on the other hand, yeah, that's true. But at least it turns out in many cases, I mean, if you start with complex manifolds, you can put scalar metrics with certain curvature restrictions. You can prove it's Kobayashi hyperbolic, but it's quite a there are hardly any results asserting that it's the Cartesian metric exists. Scalar metric with negative curvature and stuff like that will ensure it's Kobayashi hyperbolic. Yeah, that's why I said in the manifold context, to have bounded holomorphic functions is a very stringent thing. Here, of course, yeah, this I'll be coming back to again. This the distance when we talk about this either Kobayashi or Kara-Theodori on a ball in Cn. Well, in this case, it's just the disk in C. It will turn out to coincide with the standard, the Bergman metric, which is also the complex called the complex hyperbolic metric, the Kähler-Einstein metric. Everything coincides on the ball. Well, in this case, it's this. Now, these are general things. So this, the Kobayashi metric is distance is always greater than or equal to Kara-Theodori distance. And both of them satisfy, this is the reason why they're extremely useful as compared to, for example, the Bergman metric. It's that we automatically, just from the definitions, we have the Schwarz lemma, that any holomorphic map is distance decreasing. While, of course, one might argue that the whole definition is set up so that this is self-evident, but still, it's useful. And now, this, whatever I said is, so yeah, if I should have mentioned that in general, it's not evident that this, when I do this infinitesimal thing, that I'll get an actual Pfinsler metric, Pfinsler norm. So in other words, the norm of a non-zero vector should be positive. That's not so evident. So if the domain is a bounded domain, so a huge class of examples where these notions are useful is if omega is a bounded domain, then dk omega. Distance functions. In other words, this is right. But the remarkable thing about this matrix, which is not at all evident on first sight, is that something very special happens here, which from a differential geometric point of view is something which rarely happens in when you're dealing with manifolds with Riemannian metrics and so on. Namely that if you start with a convex domain, it turns out that there are lots of complex geodesics, which are from the geometric point of view, totally geodesic embeddings of the Poincaré disk inside the manifold. So let me just say a few words about this. And here I have not yet talked about, well, I do mention convex towards the very end, but this notion of complex geodesic, of course, makes sense in general whenever the metric is defined. So as I've explained there, it's just a holomorphic and isometric embedding from the, here I suddenly switched from the disk to the upper half plane because Markovitch, at some point I have to refer to Markovich's papers. So there it works with the domain being the upper half space rather than the disk. It's a matter of choice. So now I'll consider maps of the upper half space with the corresponding Poincaré metric on that. So the complex geodesic is a holomorphic and isometric embedding. Well, that's it. But the key point here is this isometric in the sense of distance functions. There are two notions of, when you have a Finsler metric, there are two notions of isometry one can demand. The weaker notion is just that you can have an embedding which preserves the Finsler norm. That would be considerably weaker, because the distance between 2 points in the image measured with respect to the disk might be substantially more than measured with respect to the ambient domain. It's just like, imagine that you have the sphere in Euclidean space. The induced metric on the sphere is just the Euclidean metric, induced Riemannian metric. But the distance on the sphere is grossly different from distance in Euclidean space. If you want a distance preserving map of a submanifold, that in Riemannian geometry is called a totally geodesic embedding. In the Euclidean context, that would be just affine subspaces sitting inside Euclidean space. Here, so we are asking that, this is a complex geodesic. Why this word complex geodesic? Well, it's clear enough. What is an actual geodesic? Geodesic is a curve which whose length between any two of its points realizes distance. So from the metric point of view, a geodesic is just a map of the real line into the metric space. So it's metric space or Riemannian manifold, whatever. So it's possible to talk about geodesics even in just metric spaces. So but here of course, it's not a one-dimensional object, it's a two-dimensional object. As noted above, the Kobayashi metric is the distance function of the hyperbolic metric and is isometric to this thing. Of course, this is a definition, but the amazing thing is that this was due to Lempert, and Lempert proved it for strongly convex domains with C2 boundaries. Subsequently, Royden and Wong generalized it to arbitrary bounded convex domains. Sorry?
Actually, there's a specifically less well-known case by them in which already, as long as the domain is bounded, the existence of complex geodesics is established. What the Royden Wong establishes the pattern one shot rather than first showing the different result for
strongly convex.
domains and then using an exhaustion.
Yeah, in fact, their argument is different, I believe. Yeah, it's a more functional analysis based argument. Yes, operator theoretic argument. And complex geodesics exist in abundance. So I'll just say in the next slide what abundance means in this. When omega is a bounded convex domain. Now, what is so remarkable? Well, at least for me, there are two things. One is whatever condition one may impose on omega, it's not at all evident that such things exist. Other than if you have very strong conditions like it's a homogeneous domain with lots of symmetries and so on, to have a general criteria which will ensure the existence of this is quite remarkable. Second thing is this condition, convexity, is first of all not a holomorphic complex geometric condition. As we know that a convex domain need not be, if another domain is biholomorphic to a convex domain, the second one need not be convex at all. It's a purely affine property, unlike pseudo-convexity, which is an intrinsic complex geometric notion. So why this convexity condition even links up with this rather intrinsic notion itself is something quite interesting. That was Lempert's original discovery. Yeah, subsequently he relaxed it quite a bit. Even this, yeah, that is even weirder actually, that notion of linear convexity. Well, yeah, so here's what I mean by abundantly many complex geodesics. So two natural things happen. Namely, if you're given two distinct points, then there is a complex geodesics passing between those two. That's all that I'm saying. Yeah. So here's your convex domain and you have 2 points. Here's the upper half space. So we can find a complex geodesic which sort of contains these two in its image. And the other natural thing one can ask for is that if you're given a point, as usual, there's a dichotomy. Either you can start with 2 points or a single point and a tangent vector at that point. Both are okay. So if you have a point and a tangent vector, there exists a complex geodesic which passes through that point and whose velocity vector at that, well, velocity vector of the map tau is along the direction v. So given a point and I can fit, this is exactly like the real geodesic in Riemannian manifold situation. No, T of course, no, T cannot be taken to be 1. See, it depends, what do you mean by this? This is just d tau acting on the vector E1. So since it's an isometric embedding, I mean, you can't expect V to be, if V has norm 1, then okay. Otherwise, T can't be taken to be 1. T basically depends on the Kobayashi norm of V. So there's one thing which I'm omitted, like, which is namely uniqueness. Are there unique geodesics and so on? Well, that actually is not going to concern us so much, but the point is that that has to do with whether the domain is strictly or strongly convex or not. The prototype for a convex domain, 2 extreme cases are the bidisk or the polydisk and the ball. I mean, if you want to see what drop strong convexity, just look at the polydisk. So here, you can have multiple, so basically you can have, there's no uniqueness in general, but you do have existence. And in fact, this was proved for, all right. But as Gautam points out, Lempert himself apparently dealt with arbitrary convex domains, but via this exhaustion by strongly convex ones. Well, this is not the end of the story. So in fact, it turns out that, amazingly enough, while this kind of properties are very difficult, other than convex domains, there's no other class of domains. One has to really look hard to find domains in Cn for which this property holds. So there are few isolated examples, but strangely enough, something which is constructed in a far more difficult, far more sort of complicated way. Teichmuller space will turn out to have both these properties. But what will be missing is this second part. This is the other major. Second major result proved by Lempert is the existence of holomorphic retracts. So when you have a complex geodesic, then you would like to, in topology, retract is a map which would, if you have a subspace of a topological space, you would like to map to the subspace in such a way keeping that the points on the subspace fixed. Well, it's literally the same thing here, except that I'm not talking about retracting onto the image of this, but for convenience, I'll define it like this. There exists a holomorphic map in the reverse direction, so that the composition of this with this is the identity from here to here. So you put the upper half space here and then you go back to the upper half space, undo the effect of tau, so to say. The thing, well, apart from various other reasons, why it's interesting for us is that this immediately, the existence of this implies that the Kobayashi and Carthodori metric coincide for a convex domain. Fortunately, this is a one-line calculation which I can quickly show. It's basically just Schwarz lemma applied twice. So, so given the existence of a complex geodesic and a retract like this, I want to get the corollary. So let me start with 2 points PQ here. And then, so I have my upper half space Z1, Z2, then PQ here, tau, and then this. Well, let's just look at that equation. So phi of so this is, well, phi takes PQ back to Z1 and Z2. Now, and the other thing we need is that on upper half space, both these metrics are the same. I have this. So let's apply Schwarz lemma. Well, first I'll apply it to this map. Distance between phi of P, Q, well, which distance? So let me say the Carthodori distance. The image less than or equal to in omega of PQ. Well, this, of course, this is just. Now, as far as this is concerned, now I'll apply Schwarz lemma to this map. So this is less than or equal to. Actually, I can just work with Cartesian metric everywhere, I guess. Oh, yeah. Sorry? Yeah. Yeah, well, I can put it like this. I mean, I can just say that this is less than or equal to this. Ultimately, I want to show that this equal to this, right?
Just from the definition.
It is.
P is a holomorphic map into H.
Mm-hmm.
So Theodore is at least as much, at most as much.
Yes.
But this is equal to the Kobayashi.
Which one is equal to?
The number you get is equal to the Kobayashi distance because you have a Kobayashi distance.
Yeah, that's right. Actually, yeah, right. I mean, in fact, what I'm proving is that you don't even need to know. If you just have a holomorphic map tau from here to here and a retract, yeah, a priori you don't need to know that this tau is a complex geodesic. So this, if you just have holomorphic, a pair of maps from disk to this and a retract, even without knowing the distance preserving property, that follows immediately just from this fact, this chain of inequalities here. So this is less than or equal to dk h z1 z2, and then these two are the same, the k and the c on h. Here z1 z2, here z2. So these two are the same, so everything else inside. So in a way, the whole business of this apparatus of complex geodesics and retracts is quite easy to state. Of course, it's another matter to prove their existence. You have a map, holomorphic map of a disk into upper half space into the domain, and a retract map that will give lots of nice things. Well, this is going to turn out to be crucial. This is something that will not be true for Teichmuller space, as it turns out. Now, here is something which is totally unrelated to all this, but this was, at least from CU's point of view, this was one of the motivations for making this conjecture in the first place. So, for some reason, it's not clear to me what motivated Yao to raise this question, but Yao had in one of his problem lists raised this question that the key word here is this class of domains, the bounded symmetric domains. In a way, in some sense, they're the best possible domains. They, from a geometric point of view, they correspond to Hermitian symmetric spaces. So they come with a nice transitive Lie group action, or semi-simple Lie group, and metric, and so on. Scalar metric, and so on. But and moreover, they are all classified. One knows exactly what this class of domains are. So from the complex analysis point of view, these are domains such that every point in the domain has an involutive automorphism. With that point as the isolated fixed point. So given a point P in omega, there will be an automorphism F of the domain with F squared equal to identity, and the only fixed point is P. But yeah, that definition doesn't really shed much light on the significance. The point is that they correspond to Hermitian symmetric spaces. Anyway, so the thing is,
It already shows that by nature of construction can move any point of another.
Yes, transitivity becomes clear. Yes, transitivity becomes clear. Yes, that's right. But it's much, much more than that. I mean, in the sense the full automorphism group is a semi-simple Lie group and so on. They're completely understood. Well, I guess the one reason for this conjecture is that it is known that any bounded symmetric domain can be realized as a convex domain in CN. It's called Harish Chandra's embedding. Comes about via representation theory. So these, well, there are various descriptions, but point is they can be realized, they can be embedded as bounded domains, bounded convex domains. So in some sense, Yao was asking for the converse, but the converse is really not, it's clear why it should be true. What converse in what sense? Well, the point is that if you start with a bounded symmetric domain, as I said, the automorphism group is transitive and so on. But more than that, there are discrete subgroups of the automorphism group. I said that the quotient, the orbit space, is a compact complex manifold. So in other words, they're called uniform lattices. So there exist uniform lattices in the automorphism group. This turns out to be a very strong property, that if you have a domain which covers a compact complex manifold, it's already something very special. And well, if you in addition you have convexity, one already knows that there are such examples, namely the bounded symmetric domain. Of course, it's not evident that if you start with a bounded symmetric domain, that there is such a gamma, that itself is a separate result. But let's assume that. So Yao's thing is that, well, that pretty much characterizes bounded symmetric domains. It is convex and it has a compact quotient when you act by a discrete subgroup of this thing, automorphism group. The key thing here is that there is no smoothness assumption on the boundary of this. So the normal techniques of multivariable complex analysis are sort of go for a toss. So of course you have this strong condition of convexity, but in fact, if there is such a discrete group acting on it, one can always expect, in a precise sense, the boundary to be extremely wide. At most Lipschitz or something like that. Or it won't even be C1, let alone any other higher regularity. So this, one has to work without any boundary regularity assumptions. And Frankel developed some very nice, ingenious scaling method. There are lots of scaling methods, and well, there is one major scaling method due to Pinchuk in multivariable complex analysis. But that, in the original form, used smoothness of the boundary. You need a defining function, C2 defining function for the boundary and so on. Frankel was ingenious, found an ingenious way of dispensing with that. Of course, he had to use this, the fact that you'll approach the boundary along a orbit of this gamma action. If you approach along this special orbit, then even without boundary regularity, still you can scale. So I'll have occasion to refer to this kind of thing, because in my work with Shubhajay, we do need some such scaling. So for now, that's one part of the proof, Frankel's proof, the major part. He uses scaling to say that you can actually, automorphism of omega contains, the dimension of the automorphism group is at least 1. Yeah, a priori we know there's only a discrete group of automorphisms. But then he produces a 1-parameter family of automorphisms. No, real. By the way, these are not complex, the automorphism group will not be a complex Lie group. They're just real Lie groups, yeah. The point is, starting from dimension 0, automorphism 0, for all we know, this might be the full automorphism group, gamma. But he says, no, there's actually the dimension of this is at least 1. And then subsequently, using that, you generate a large automorphism group. Then you show that it's actually a semi-simple Lie group, a bunch of stuff. But the main thing is the first step as far as, well, according to me. Yeah. Now, this remark is important. So it's unknown. So here the key, one of the key assumptions is that the quotient is compact. Now, if you have seen stuff in like Mosto rigidity theorem and so on, many of the things which are stated for compact manifolds go through for finite volume manifolds. So it's natural to ask if this result, instead of what I mean here is if this result is true, I forgot to write is true. It's unknown if this result is true, if the assumption of compactness of omega mod gamma is relaxed to finiteness of volume with respect to some, I mean, volume in what sense? Well, whatever sense it's okay, there's no result anyway. So the point is, one natural way is that you look at some intrinsic metric here and say a Hausdorff measure, n-dimensional Hausdorff measure, or any reasonable sense of finite volume is okay, but the thing is, it's not known.
I don't recall actually what, remember exactly what was that. It's just omega.
Yeah, well, in the last year or so, there have been a couple of papers which have tried to address this, but even Zimmer's, they don't really touch upon the heart of the matter. I mean, they make some very strong assumption that, for example, the identity component of the automorphism group is positive dimension or some such thing. The whole point is to, yeah, the whole point is to go beyond discreteness. If you start putting additional, there are still non-trivial results, whatever they do, but they don't touch up. The real thing is still open. Which one? Yeah, exactly. Yeah, exactly. Yeah, yes. The starting step is to get a one-parameter family of automorphisms. So this is well, it's not. It seems like a non-trivial question actually, though it superficially it looks like this. And Frankel's result is by now it is at least almost 20 years old. $1990, I thought. Oh, yes. Yeah, okay.
But you are not wrong.
Okay, now let's see. Okay.
5 minutes early.
Okay, so
We have about 20 minutes.
I have 20 minutes. Okay, that's good enough. Yeah. So let's now, well, of course, I say preliminaries, but preliminaries to what? Well, that's the Teichmuller space part. Now I'll shift attention to that's whatever I had to say about convex domains. The point is, as I said, I would like to sort of put the context of this. Why would one expect Teichmuller space to be biholomorphic to a convex domain? That's one point of view. On the other hand, as you mentioned, conjectured the contrary. So why would one expect otherwise? Both of these are captured in the results I've stated. What would make it seem plausible that they are biholomorphic would be the complex geodesic stuff. On the other hand, Frankel's result in the finite, even though the finite volume case is not known, would make it seem unlikely. Which one?
The theorem you're about to.
Not quite, because this is Yeah, the whole point is the mapping class group action on Teichmuller space has a quotient, the moduli space of Riemann surfaces, which has finite volume. Yes, Weil-Petersen, Teichmuller metric, any of those. Yeah, but that.
With the convex domain, it's coaction.
Yeah, but we don't know that, right? Yeah, that's right. So
They're not.
it's not. But how does it? So it doesn't. See, if we knew the finite volume version of Frankel's theorem, we could immediately conclude that Teichmuller space cannot be a biholomorphic to a convex domain. The logic goes the other way. Yeah. Scaling. No. Here the point is, in order to do scaling, either you should have a sufficiently smooth boundary or you need some assumption like convexity. This Teichmuller space is going to be bad in both senses. The boundary will be extremely complicated, and the whole point is that it's not going to be locally convex anyway. So you'll you assume that it's convex and then do scaling. That's how you get a contradiction. Yeah. Well, so let me start by defining recollecting some basic definitions from Riemann surfaces. So X will be a compact Riemann surface of genus greater than 2, Kx the canonical bundle of X. So this is just the bundle of holomorphic one forms on holomorphic one forms on X. No, not holomorphic. Yeah, there's 1-0 forms. Yeah. Let holomorphic quadratic differential on X is a holomorphic section of Kx tensor Kx. Classically, well, it's just written as dz squared times something multiplied by a holomorphic function in local coordinates. I don't know whether I'll actually be needing all this, but let Qx be the space of holomorphic quadratic differentials on X. The point is, when I look at the space of all complex structures, this has a natural interpretation. If you take a point in the space of all complex, space of all Riemann surfaces of a fixed topological tape, if you take a specific Riemann surface X, this has a natural interpretation as the cotangent space to the deformation space at that point X. Beltrami differential is on this and so on. Well, Beltrami differential on X is a L infinity section of Kx inverse tensor Kx. We denote the space of Beltrami differentials on X. In a holomorphic chart, it has this form. This is the way classically it was thought of. It has this very weird expression dz bar by dz multiplied by mu. Yeah, it's an endomorphism of the canonical bundle. Is a more natural. Well, the uniformization theorem, I don't really need this, but X will correspond to H mod gamma for some Fuchsian group is by definition a discrete subgroup of this PSL2R. Here is the more important thing. The whole point is you fix the topological type of the surface. Then you ask, how do I parameterize all possible complex structures? That's the starting point. The whole point is that given compact Riemann surface has many possible non-equivalent, non-biholomorphic complex structures. How do I sort of describe the space, the set of all such complex structures? The thing is, even though of course, here all along, one should keep in mind that topologically, all of them are the same. It's fixed, the genus is fixed. But even though the complex structure on X and Y may be different, it turns out that there are something, so by definition, there cannot be a biholomorphic map since the complex structures are different. But still, there is something which is called a quasi-conformal map. It's a topological homeomorphism. Now, this is the analytical definition, sort of. There's a more geometric definition in terms of distortion of ellipses and so on, of a quasi-conformal map. Though, for practically working with, this is the more useful thing. Analytically, it's a homeomorphism with weak partial derivatives that are locally L2. And the point is that this Beltrami differential satisfies non-mu less than 1. Now, the thing is that if this Beltrami differential is actually equal to 0, that would mean that this numerator is 0. So that it would mean that f is at least weakly holomorphic. Combine that with locally L2, one can actually prove that it's really holomorphic. So this vanishing of this measures, well, the norm of this measures how far it is from being holomorphic. From this perspective, one can define Teichmuller space by considering quasi-conformal maps from a fixed base point up to homotopy or isotopy. So what one does is, what is fixed is this x. In the previous slide, I talked about this x. So, So here you look at pairs. This is you look at pairs, not just another Riemann surface, but one with a specific quasi-conformal map from here to here. Now one can check it turns out that if you actually have a smooth map, I said a quasi-conformal map is a homeomorphism. But if one starts with a diffeomorphism, you can check that it's automatically quasi-conformal. Any C1 diffeomorphism will be quasi-conformal. So there are quasi-conformal maps between in a very trivial sense. So if you have but one wants the map itself actually. One wants to keep, this is called a marking. So you have not only do you have another complex structure, you have a specific map. This pair is called a marked Riemann surface, and then you declare two such pairs to be equivalent if and only if there's a conformal homeomorphism. In other words, a biholomorphism from Y to Z, so that this composition from here to here, forget this lift and so on, the composition should be homotopic to the identity map. Now, why do we make a fuss about this homotopic to identity map or not? We get a natural action actually. So let's see, where is this? First, I still haven't put any topology on this, by the way. It's just a set. This TG is just a set of all such pairs with some equivalence relation. One way to, so let alone a complex structure, I haven't even put any topology or a manifold structure. So, but fortunately, there's a nice notion of distance. The Teichmuller distance between two marked surfaces, x and y, is defined by, as can be expected, if that Beltrami differential mu, as I said, if there's a homeomorphism between two surfaces with very small Beltrami differential, then it's like saying all the complex structures are almost the same. So the smallness of mu should be in some sense. And that is, instead of working directly with mu, one defines this so-called dilatation. So if mu is 0, which would correspond to a conformal map, this would be 1 and the log would be 0. So the distance would actually be 0. So this sort of captures how close the complex structures are to each other in terms of dilatation of the quasi-conformal one. And it in fact turns out, though it's not needed for us, that to say it's a distance one would need it, I guess. The infimum, Teichmuller, way back in 1930s, proved that he was the one who developed this whole theory, actually. He proved that this infimum is actually attained by an optimal quasi-conformal map. There is one. The optimal one would be the one with the smallest mu. The Beltrami differential should be as small as possible, and that is, in fact, there does exist such a thing. No, it's like, I think it's, yeah. What was the name? How do you spell it? Rauch. Oh, Grouch. Oh, yeah. Well, yeah, okay. This is a very murky area which seems to elicit some very passionate reactions, because Teichmuller was a controversial guy after all. So, as far as I know, this Teichmuller proved it, but I might very well be completely off the mark. So, yeah, right. The good thing is this, at least this gives us a topology. Well, that's not the only significance of this, but for now it gives us a topology, and then subsequently the next giant in this area is Lippmann-Burs, more or less Lippmann-Burs and Alfors. Lippmann-Burs proved that this can be embedded. Here right now it's just a topological embedding. So we have a topology, the metric topology, and this can be embedded as a bounded contractible domain in this. Of course, since it's only topological embedding, this bounded really doesn't have much value. I mean, you can embed it in this thing. You can always deform the embedding to go inside the ball. Topological, yeah. But why
not preserved.
Metric, well, the target, what metric would one consider? If this is the Teichmuller space comes with this thing?
Yeah. CN has its own metric, of course.
You mean the Euclidean metric?
So it's not
No, of course not. I mean, this is the intrinsic metric. This turns out to be the Kobayashi metric.
Oh, okay.
This is so as you go towards the Teichmuller space, it has a bounded domain. So you go towards the boundary, it will like you're going to infinity. Now the thing is, as I said, bounded in this statement doesn't have much value if you're just talking about continuous embeddings. But why I put it is that the point is Burs embedding is it's not a single embedding. You have to fix a base point. Then corresponding to that base point, you get an embedding. What he proves is that the complex structure induced on the target domain is independent of the embedding, and all of them are bounded domains. So in that sense, there is a well-defined complex structure. We regard, but for now you can just ignore this bounded, you just say some embedding as a domain in C, and then you can always shrink it, get a bounded one. We regard, but that way of defining it is, there are many ways of shrinking a domain. So which complex analytically you'll get huge variety of stuff. So that's very unsatisfactory. The construction itself should give rise to the complex structure. And that is, in fact, that's what happens. Burs proof itself gives it as a natural bounded domain. You don't have to further compose with any homeomorphism. We regard Teichmuller, well, I forgot space, as a complex manifold with the induced complex structure induced from CG minus 3G minus 3. Now, here's, okay. So let me just finish this one slide actually. That's so, as I said, I would like to compare two aspects of the complex geometry. One is complex geodesics, the other one is this automorphisms, discrete group of automorphism. What kind of quotients do I get? So this Teichmuller space comes with a natural group of automorphisms. The mapping class, the so-called mapping class group, this is a group of homeomorphisms of S. So here S denotes the underlying fixed topological surface. When I use complex structure, I won't use S anymore. I'll use X comma F, a complex structure with a marking. So, but this is by definition just the homeomorphisms of the topological surface. I have to put orientation preserving, I guess. Homeomorphisms of this up to homotopy or isotopy. So I say that two things are the same if they can be continuously deformed to one another. So the good thing is that what this does is if you start with a pair in Teichmuller space, a point in Teichmuller space, which is by definition a pair, a Riemann surface with a marking. So you compose one such thing, an element here, keeping the Riemann surface the same, but you change the marking. So that gives a different point in Teichmuller space. The marking has changed. The underlying complex structure has remained the same. So, and in fact, one can check that the way Baer's embedding is defined, that every such thing is actually a holomorphic map. The isometry part is clear by Teichmuller's definition, but it's actually this action by mapping class group on Teichmuller space is actually a holomorphic isometry of this. Ramanujan proved much later on that, so this is actually from complex analysis point of view, this is the real significance of the Teichmuller metric. It's actually the Kobayashi metric. Of course, the interesting thing is the Kobayashi metric requires one to have a complex structure even to define it. This one we were able to define even without anything. We didn't even have a topology actually. So, but they're the same. And that's one thing. The other thing is that the full automorphism group, or for that matter, the isometric group of the Kobayashi or Teichmuller metric, is just this, there's nothing more. Already said that the action of MCG is by holomorphic isometries. They're both automorphisms and isometries. But Ramanujan proved that there's nothing more. Any automorphism or isometry of Teichmuller space has to come from a mapping class group action element. Okay, I'll stop here.